Hi, so I'm Daniel Hellstrom from Cobham Geisler, the developers of Leon 3 and Leon 4 processors. I'm from the software side of Geisler. We are doing tools, simulators, hardware debuggers, compilers, and also we do operating system support, such as operating system drivers. I'm here to present the ESA project that Cobham Geisler implemented. So this is a quick outline of what the project and what I'm going to present today. So basically, the JUICE mission is a satellite which includes a number of instruments. ESA identified that 10 instruments as potential users of a common software and hardware platform. So ESA gathered common requirements for the hardware and software, and then gave that to Cobham Geisler, and we developed a Leon 3 based DPU, and we also made software in terms of boot software with Spacewire networking and drivers for the 712 for bare metal and RTEMs. So I will be talking a bit short about the ESA mission, the project overview, and a bit about the hardware background and the results. I will go quickly through that. Then some boot software, the driver, and the tools we used during our development, and some conclusions. So the JUICE mission is a L-class, large class mission from ESA. It's planned launch in 2022. It's going to Jupiter. On board the satellite, there's a 100 megahertz Spacewire network, and the instruments that we are focusing on have two different redundancy schemes when it comes to Spacewire. Either you have one DPU and with two Spacewires each, or you have two DPUs with one Spacewire each. So software needs to cope with that, and also the hardware design. There's a push protocol over CSTS over Spacewire. So the project started in February 2015 and ended in March 2016, where the hardware was finalized and the first deliverable software was completed. Then we have got some follow-up extensions to this activity, two as a matter of fact, where there were newer requirements and new services. And in this last extension, it's just the first part of it just completed. So the slides are a bit outdated because it was finished in December. ESA will take the software to ISVV and also do a compatibility test of the Spacewire network with the hardware and software platform. So on the left-hand side, you see the sections, the different parts of the DPU processor, and the software that comprises of boot software, standby software, software drivers, and we also made some improvements to the TSIM simulator during the project. So ESA gathered a lot of requirements. They were related to different sort of things. When it comes to hardware, it could be, for example, CPU performance or types of memory that were required, and the different sizes of these memories, FPGA interface, Spacewire cross-strapping, and radiation environments, and I/O interfaces. On the software side, requirements were related to the ECSS software engineering and quality standards that we need to follow during our development, and also a bunch of requirements from the flight computer initialization sequence specification. And also, of course, that the software should run in all DPU configurations. So the requirements were to fit several different instruments which had different needs. So hardware was supposed to be configurable. Sometimes 4 megabyte SRAM was enough. Sometimes 128 megabytes of SRAM was the target. So we needed to define a platform which could suit all the instruments. This is the final prototype with, it has EM components, engineering models. So on the left-hand side you see the 32 megabytes SRAM version, and on the right-hand side you see the SDRAM. This is the bottom side with the 712 dual core. So this is the architecture. You can see the memory architecture of the hardware design. I'm not going to go into detail, but the interesting part, I guess, is the memory is situated close to directly on the pins on the 712, and there's a buffer to the slower memories and the FPGA to offload to lower the capacitance of the address bus. Same goes for the data bus. So there were different configurations. This was the prototype, which had MRAM as boot memory, and flight models, for example, 4 megabytes of SRAM or 256 megabytes of SDRAM, and the boot memory consists of 32 megabytes of PROM, kilobytes of PROM. For your reference, there's the different component selections. So SRAM configurations varied from 4 to 32. There was a fixed SDRAM you could select instead of 256 megabytes, and the flight PROM was 32. Spacewire LVDS, capability of up to 200 megahertz. The I/O to the FPGA is either Spacewire or I/O interface. We had an option between 2 or 8 megabytes of MRAM storage as an application storage, and also GPIO to control the power down reset mode of that. So we did a bunch of different analysis, and then we identified different critical paths, and those paths were analyzed using the Hyperlinks simulation from Mentor Graphics. So it turned out that we had to, since you can configure the design with different memories, it became many different configurations to simulate. So in the worst case, we could see around 70 megahertz on the SRAM and 45 about on the SDRAM. So the results of the hardware is apart from the prototype board, which consists of a EM component DPU and a commercial component motherboard, is the output that was delivered to the instruments providers of the JUICE satellite. So there's a manual and schematics and PCB layout, and a manual to configure the schematics, different resistors, different memories to take into account when this was to be configured into the specific instruments. Also a couple of quality documents such as FMEA, radiation analysis we performed, part stress analysis, timing analysis, worst case analysis, and so on. We also did a power calculator by running the verification binaries on the CPU, and we measure different power, the different power budgets from the different test cases. So there's a Excel sheet which you can get a rough estimation depending on, say, Spacewire frequency, processor load, etc. The boot software follows the ESA flight computer initialization sequence requirements, which introduces a number of concepts like warmer start, post-mortem analysis, standby mode, Spacewire push services, and so on. The main parts of the boot software is, well, once the reset, the warmer start triggers the start, there's a processor module initialization and self-tests. There's then standby mode starts, which is responsible for Spacewire networking. And then finally, the application is loaded into main memory and the application is started. So we did unit tests and validation of this, of course, to follow the software engineering standards. We try to make a minimized boot software. So that was the goal already from the start. So we tried to use as few hardware resources as possible. For example, we disable interrupt. We didn't use FPU, etc. Now, these figures are a bit outdated. I think it requires about 27 kilobytes of PROM. I guess it still holds with 256 kilobytes of RAM. It's implemented in assembly and C language, no ADA. And we didn't have any code reuse or any code generation. It doesn't rely on any specific toolchain or any third-party library or runtime as such. It's a configurable software where you can configure it using mission specific configurations or more BSP configuration options related to the hardware setup. So the first step is initialization, which is triggered by a reset or warmer start. You would expect it to initialize the processor and I/O, and then the self-tests, which are sort of destructive in a way. It tests the I/O integer unit of the CPU, caches, memory, and memory controller itself to see that the EDAC mechanisms works. And it initializes memory, and then it finally records the results in the boot report, sets up the C environment, and jumps to standby mode. The test approach we used was to test only the hardware that was used by the boot software itself, and in order to load and start the application to avoid triggering potential bad stuff. So the memory layout is basically 4 different sections. In main memory, there's 3 sections. The lower RAM, which the application is foreseen to be loaded. Unused area, where the user can configure not to scrub the memory. And then there's a higher RAM, where the boot software is located. In the upper top, there's the time service RMAP area, where the onboard computer writes the TDP data, and there's a boot report. So instructions are located in PROM all the time, but it's quite small application, so it fits into the instruction cache. So when entering standby, there's a set of decisions based on the Spacewire link and the traffic on the Spacewire link to determine if we're going to boot directly or if we're going to stay in standby mode and communicate with the onboard computer. A boot report is sent out, and there's also a mechanism to select which Spacewire link in the case we have 2 Spacewire links on the DPU. The standby mode implements a couple of services, most of them related to Spacewire. So the CSDS push protocol, we implemented services 1, 3, 5, 6, 8, and 9 also, and 17. The memory service is service 6, which ground can upload and download applications or check memory. Housekeeping, time distribution slave is implemented. Apart from the push services, there's also a memory scrubber, which is configurable, how often and where it scrubs. It scrubs also cache and registers. There's watchdog, and there's a lot of stuff as well. So we used a very simple design. By using a cyclic executable, we split it up time in 10 different equal-sized execution slots. So every slot was given 100 milliseconds. And during our validation, we found out that we required less than 20 milliseconds per slot. So we could basically go down to 10 megahertz in the system and still meet the deadlines. Which is good because the requirement was to have a system with a minimal frequency of 24 megahertz. So when it comes to the load sequence, there's 3 different images possible. Either the application, the standby mode has uploaded a RAM image into application memory up to RAM, and that could be booted, or it's one of 2 applications loaded from application storage memory. The image, there's an image format describing each application image. There's an entry point, and there's a couple of sections, a configurable number of sections. It's similar to an ELF file in that way. And it also allows to patch the software in flight, since we can just add another section with some patches. The application software is verified in the source location when it's read out, and on the destination when it's copied up to memory. We developed a unit test framework using Tickle. And similar to other presentations a couple of days ago, we implemented different stubs, and we had a stimuli input to the different software components, and then it was verified the calls to the stubs basically, and we could return different values and see that the software component was executing correctly. We used tsim to get code coverage. We ended up with a 98% code coverage of the code that we unit tested. Then there's also another 10-20% that we took by validation instead, because the low-level boot is very low level, and it's also a linear execution path, so there's no branches, so it's no. During validation, we had a test setup of a Linux workstation. We connected the DPU board using grmon with a JTAG debug link, and we also connected a GRESP through Ethernet, and we tunnel Spacewire traffic over the GRESP, which enable us to send time codes and so on. And we also could control the reset of the DPU board through the GRESP. Then the test framework written in Tickle was basically generating, mimicking the onboard computer, sending Spacewire packets onto over the GRESP to the DPU board, and then we could verify that the response was okay and the functionality was okay, as expected. We also did some white box testing, where we ran the validation test cases, and by using grmon, we could set breakpoints at different locations and see that they were actually met, that we reached those locations, and we can also verify stuff that wasn't unit self-tested and hard to validate. So, and we also could inject errors so to see that the self-test was actually performing and reporting the correct answers on failure. We also did driver software for the 712 DPU. We also aimed for a small, compact, low-level drivers. So we didn't use any active objects, which made it possible to port it to using an OS abstraction layer to port it to the bare metal environment as well. Similar unit testing approach as to the others. We also did validation by using different test cases. And then, well, the drivers comprised of SPI, UART, timers, GPIO, HP, status register, and some other small cores. Also Spacewire, that was the major focus of the driver library, because we knew that all the instruments in the JUICE satellite was going to use Spacewire in their application. So that was the main focus. It was based on the public available Spacewire driver, the GRSPV packet driver, and we reduced the complexity of it by removing software FIFO, work, task, and interrupt processing. So now instead the user is responsible for interrupt processing. It's still the zero copy interface. The interface is quite similar to the public available driver. During the project, in the later stages, we also had some work where we were asked to improve some parts of TSIM, and we made some adaptations to TSIM to describe the DPU itself. So we could interface, well, we could basically have a script for every DPU platform configuration. So what we have added in TSIM core itself was the FIFO model of the UART, and we also have added error injection support on the Spacewire interfaces so that we could verify the well, some bad scenarios when we have errors on Spacewire, which otherwise can be quite tough to insert at the sensitive areas. And we also had some MRAM application memory timing checks so that the GPIO reset was held in a correct number of microseconds, and there's no excess in parallel to that. So another tool we were using during the software development was the GRESP from Cobham Geisler also. Already described that. We used the GPIO to control the reset, send time codes, and Spacewire packets over Ethernet. We also used, in the beginning of the project, the development board of the 712. And then later on, when the hardware was manufactured, we could do the final development of on top of the motherboard, on the real DPU in 2 different configurations. And we could rerun the validation tests and do the power calculations and so on. And see and we did a lot of memory tests to verify that the memory bus was okay in the different scenarios. So on that board, on the motherboard, there's a power measurement circuitry, and there's different power sources going in here, so we could measure the different powers from, let's say, SRAM and SDRAM and CPU independently from each other to get a better understanding. So conclusions and well, future, we are already reusing the code, parts of the code in the upcoming ESA microcontroller. That will have a ROM inside of it that always starts, and then it will read using the same application format. And then, well, we managed to define and implement the DPU matching all the requirements. And out of the 10 identified instruments, 7 instruments are using the design and software either in parts or in whole. So I think that's a good success, and it's a COBAM. Even if we develop this during the ESA activity, it's a COBAM Geiser-owned product, which means that it's not limited to ESA missions or European area. So thanks for listening. And it's no point in going to Geisler.com because it's not available on the homepage yet. So,
Okay.
but you can learn about other stuff from Geisler, the 712, for example.
Well, thank you. Any questions?
Wondering why you didn't have EDAC turned on the prom.
Because of the radiation analysis, it turned out that it was very, very unlikely. And the prom, it was it was much more radiation tolerant than the rest of the system, a factor 10 or something like that. So we discussed this with ESA, and we both came to the conclusion that it was beneficial to turn it off. It's also easier, the software implementation is much easier that way. And you get larger memory. So, yeah.
I have a simple one. So what is the power consumption approximately of the board?
Oh, that's a good question. It depends on which frequency you run it, which Spacewire frequency you use, which type of memory you use. So there's probably 50 different answers to your question. But yeah, I can dig up the power measurements for you if you would like to do that afterwards. I don't have it in my mind. It's probably in the final report, I think, available on the net.
Is this more expensive than a Raspberry Pi?
No. Yeah, this one is EM part, so it's very expensive, yeah. So, yeah, this one is, the development board is it's a good alternative to get started. Yeah.
So I guess the picture on this last slide here, that's a picture of the flight form factor. I'm just curious how kind of mechanically, electrically, your instrument vendors are taking that and integrating it into their
that's a good
electronics.
question. I mean, it's a prototype board, but we consider this area to not be part of the DPU, DPU board. So these areas you see here with the connectors, they can be cut off, and basically you could take the whole design and just place it on the instrument. But in practice, what they will do is configure the schematics and reuse the parts of the schematics and do their own layout.
Okay.
So that's the main scenarios, because this is a 12-layer board, and the instrument providers may use other technologies
So do you
available.
provide the EDA board schematic?
Yeah,
That you use?
bill of material, schematics, layout.
Well, it's one thing to have a paper, PDF of the schematic. It's another to have the EDA.
Yeah, but the EDA, yeah, for sure, yeah. Yeah, that's the purpose. So they go in and remove 0 ohm resistors. They have a manual from us stating different functions, and then they can go in and say, okay, I need 2 space wires, I need this and this, and then it's a manual how to remove parts of the schematics or add to or something like that.
I was wondering if the Spacewire IP on this board is the same that is used in the UT700, and if then your driver modifications would be applicable to that device, and if they would be available.
Yeah, UT700, it's the same IP. There might be a bit or two that's different, but yeah, it's the same. The UT699, on the other hand, it's not exactly the same IP.
Okay. Any more questions? No? I guess. Thank you.
Okay.
Thank you.
Thank you.